Hello, I'm François Daoust. I work for W3C, where I keep track of media-related activities. The goal of this presentation is to take a peek at mechanisms that allow or will allow media processing on the web. I will very hardly touch on machine learning per se, just as a possible approach that people might want to apply to process media. Slide 2. In the past few years, I would say that standardization has enabled 4 different media scenarios on the web. First one is support for basic media playback, also known as progressive media playback. In other words, the ability to play a simple media file. This was enabled by the audio and video tag in HTML and the underlying HTML media element interface. Second scenario is support for adaptive media playback. Here, the goal is to adjust video parameters, typically the resolution, in real time to the user's current environment. The scenario was enabled by Media Source Extensions, or MSE for short. It brought professional and commercial media content to the web, and MSE is by far the main mechanism used to stream media on-demand media content on the web today. Third media scenario is different. It is about real-time audio-video conversation. It was enabled by WebRTC, and WebRTC is also used to stream media in scenarios that require latency to be minimal, for instance, cloud gaming. Fourth media scenarios is also completely different. It is about synthesized audio playback to generate music or sound effects in games, for instance. This was enabled by the Web Audio API. Slide 3, the actual media content depends on the scenario. We're talking about files for progressive media playback, streams for adaptive media playback, individual media stream tracks for WebRTC, and short audio samples for Web Audio. Slide 4. In a typical media pipeline, media content gets recorded from a camera or microphone, encoded to save memory and bandwidth. Then different media tracks are muxed together, and the result is sent to the network. The decoding side is roughly symmetric to the encoding side. Media content needs to be fetched, demuxed, decoded to produce raw audio and video frames, and rendered to the final display or speakers. The mux and demuxed operations are only needed in progressive and adaptive media playback scenarios. WebRTC deals with individual media stream tracks directly, so no mux and demuxed operation per se there. In the interest of time, I will mostly focus on the decoding side, but some considerations apply to the encoding side as well. Slide 5. So where would people want to process media streams? Well, they may want to analyze frames to detect objects, faces, or gestures, or they may want to actually modify the streams in real time, either to add overlays, for instance, to add funny hats, remove the background, or simply because the client application is actually a media authoring tool. Slide 6. In most cases, these scenarios need to process individual decoded audio or video frames. So if we look back at our typical media pipeline, ideally we'd like to hook processing between the record and the encode operations on the encoding side, and between the decode and the render operations on the decoding side. Okay, so slide 7, let's get back to our 4 media scenarios. For progressive media playback, the HTML media element takes the URL of a media file and renders the result. The browser does all the work, and that's too bad because that means there is no way to hook any processing step there. Slide 8, but you can cheat. You can create your own processing hook. For video, you can copy rendered frames repeatedly to a canvas, process pixels extracted from the canvas, and render the result to another canvas. The solution is not fantastic because it's not very efficient, but at least it exists. Slide 9. MSE is essentially a demuxing API. In other words, it allows applications to take control of the demux operation and by extension of the fetch operation. MSE does not expose decoded frames, so no processing hook either, but the same canvas hack can be used. Slide 10. For WebRTC, first remember that there is no demux operation. WebRTC takes care of the fetch and decode operation. So in theory, that's fantastic news. We should get decoded frames out of WebRTC. However, in practice, a decoded stream in WebRTC is represented as an abstract and opaque media stream track object, and the actual contents of the decoded audio or video frames are not exposed to applications. So back to the same canvas hack again. Slide 11. The Web Audio API is a processing API at its heart. However, the whole API is meant to process an entire file. There is no support for streaming and no indication of progress when you process a large file. This works well for short audio samples. It's really not a good fit for streaming scenarios. Slide 12. In other words, today, the only way to process audio is through the Web Audio API, and that is only really useful for short audio samples. And the only way to process video is by capturing a rendered frame onto a canvas, which is not very efficient. Slide 13. I lied. There is another way. A web application may also choose to implement the entire media pipeline on its own, using JavaScript or WebAssembly, and render the result to a canvas. This is suboptimal, especially on constrained devices, but you know that some media authoring applications actually do that. Slide 14. If existing solutions are not efficient enough, what would make media processing efficient? It essentially boils down to sizes. To give you a rough idea, a single video frame in a full HD video weighs about 24 megabytes. So processing a full HD video in real time means processing about 600 megabytes of raw data per second. Any efficient solution should avoid having to manipulate or copy bytes around, while allowing to leverage the CPU, the GPU, WebAssembly, machine learning hardware, while also giving some knobs to control the processing speed, and last but not least, while also keeping related tracks synchronized. That's a lot of requirements, and the list is not even exhaustive, so that typically explains why decoded media has remained opaque until now. It is hard to expose decoded media on the web. Slide 15. It is hard, but it's not impossible. The WebCodecs API, initially proposed by Google, aims at providing access to built-in media encoders and decoders. As a byproduct, the API exposes decoded frames, allowing applications to hook into the output of the API to process these frames. Note that the API does not take care of the mux and demux operation, which will have to be done by the application through some JavaScript or WebAssembly code. This shouldn't be a problem in practice. These operations are not really heavy on the CPU. Slide 16. The API is very much in flux, so it's hard to assess anything on WebCodecs for now. There are a number of open questions, starting with how can WebCodecs be integrated with other specs? WebAssembly, MSC, WebRTC, WebXR for rendering video in immersive context, and of course, integration. The integration question also exists for machine learning APIs. WebRTC, it's worth noting that the WebRTC working group has started to work on WebRTC insertable streams using insertable media using streams, which should eventually build on top of WebCodecs. By the way, it seems also worth noting that WebCodecs is not based on WebWG streams. That was the initial goal, but turned out to be very difficult. So having a way to process WebWG streams does not necessarily mean that it will be de facto possible to process media streams. Incubation takes place in the Web Platform Incubator Community Group. The Media Working Group may adopt and standardize the proposal once it's ready. Slide 17. Before I conclude, I'd like to raise a few other media technologies and proposals that may or may not affect the way processing gets done in the future. For instance, the Media Working Group standardizes a codec switching feature for MSC, for instance, to allow to insert an ad which may be in low resolution in the middle of a 4K video. How would such a switch affect processing? So in some processing scenarios, all that may be required is rendering an overlay on top of a video without touching the video itself. That is precisely what the HTML video element.request video frame callback proposal is offering. How does that affect everything that I presented so far? Flat videos are no longer the only videos in town. Other types of videos get rendered for VR and AR and more immersive experiences. This includes 360 videos, volumetric videos, and more generally, 3D playback experiences. How does processing apply to these cases? So, I have only focused on audio and video tracks, but media content also contains event tracks that are more and more used to control the playback experience. Media industries are putting a lot of effort these days to standardize solutions to expose media timed events to applications. The generic idea is to rely on user agent to do the work. If WebCodecs requires applications to demux media contents themselves, then what happens to events tracks? One final note on encrypted media. In general, the goal there is to hide the bytes from the application, so encrypted media is normally not a good candidate for application-controlled processing operations. There may still be scenarios where the ability to process encrypted media in a separate sandbox may be useful, so something could be worth keeping in mind. All of these features and others are mentioned in the overview of media technologies for the web, which I invite you to take a peek at. Slide 18. So what I have tried to convey here is that exposing decoded media frames to application is doable, but not easy, or not as easy as it might sound. There is no satisfactory solution today. WebCodecs seems very promising, but there are lots of open questions that still need to be discussed. In order to be successful, the work on WebCodecs would greatly benefit from coordination and engagement from people involved in other technologies. And that includes people looking at exposing machine learning capabilities to web applications. Okay, I'm done. Thank you. Bye.